Okay, so let's get started. So this class we're going to continue our discussion on the aerosol size distribution measurement with an SMPS. Okay, so let's do a quick recap at the beginning. So last class we briefly introduced how the SMPS is composed of. It contains a electrostatic classifier, a differential mobility analyzer, and a condensation particle counter, right? So we briefly introduced how we are going to convert the the information that we obtain from the SMPS to the size distribution. So basically, to conduct this conversion, we need to do a two-step process. So first, let's still briefly go through the diagram. So what happens is that the ambient aerosol samples, or it can be aerosol samples from any reactor system, will first go into a neutralizer, right? So inside the SMPS, it can be radioactive materials, or it can be made of soft X-ray, or based on the talk from Dr. Jian, it can be the natural ions, right? It's just the ions in our ambient. And then after these particles are charged with certain uniform charge distribution or a known charge distribution, they'll be introduced into this differential mobility analyzer, which contains an inner electrode and an outer electrode, right? So this is the inner one, outer, right? And because of the electrostatic force or the electric field that's built between these two cylinders, the particles will become separated because different particles will have different electrical mobilities, and electrical mobility is dependent on particle size, right? So after the particles are further collected, right? So then these classified particles are being introduced into the CPC, where we count their number concentration. So further, by scanning the voltage that's added onto the inner electrode, we can classify particles from the small size to the large size, where we can further calculate the size distribution. So then we ask the question, how do we convert the measurement to the size distribution? We mainly spend a lot of time talking about how to convert the DMA voltage to particle size. So to do that, basically, what we did is that we derived this analytically, right, dr dx, and further by considering the time, and then further considering the flow condition, we could derive what's the relationship between Z and voltage, right? And further, Z is related to particle size, okay? So to sum that up, basically there's a one-to-one correspondence between the voltage that's added onto DMA and the electrical mobility, and that is shown by this equation. And then further, the mobility is dependent on the particle size, right? So because of that, if you, let's say, set up the voltage, the DMA voltage, to be 1000 volt, and further, if you know the flow rates and the dimension of the DMA, then you can calculate what is the electrical mobility. And further, by assuming different number of charges on the particle, right? It can be +1, +2, +3, +4, then you can convert it into the electrical mobility size, right? So basically, you can calculate what is the electrical mobility size of a particle that corresponds to this 1000 volt voltage, right? So then to convert the SMPS measurement, we also need to convert the CPC reading to the concentration, right? And especially for measuring the aerosol's size distributions, it's not only about concentration, it's a size distribution, which is shown as dN d log 10 dp, or sometimes people also use dN d ln dp, right? So the difference between these two is just a factor of natural log of 10, right? So we'll talk about that later on, how to do this conversion, but let's say that we're trying to get this one first, right? So how do we convert the response or the number concentration that's monitored by the CPC to the size distribution, right? So to do that, we need to consider multiple factors. The first one is the transfer function. Okay, so the transfer function is basically the probability that a particle of mobility Z that we transmitted from the aerosol flow to the monodisperse sample flow. So basically, it's a probability of the particle being classified, right? So let's say if the DMA voltage is set up again to be 1000 volt, if you send in two small particles, then they will just follow this trajectory here and get collected by the inner wall. If their size is too large, then they will go downstream, right? So the probability will be 0 for these two different trajectories, right? So there will be certain mobility, electrical mobility, that the particles will follow this perfect trajectory here. It's not necessarily a straight line, right? We'll follow this perfect trajectory here to be classified by the DMA, right? So if you plot the transfer function and then further plot it as a function of ZP, so we know that there's going to be a perfect transfer function, perfect electrical mobility that has the highest electrical mobility, highest probability, and then for most of these ranges, it's just 0. And then what about this section? What about from this section to this section? Okay, so there's going to be some analysis, right? So if you want to see the detailed analytical solution to this problem, again, you should check this Knudsen and Whitby paper, which is regarded as the Bible for the differential mobility analyzers. It made this complex problem look very straightforward. But if we just give some extremes to consider the trajectory of the particles, right? So the way we can consider is just by considering the two boundaries of the inlet flow and the two boundaries of the outlet flow. So if we also start from this perfect trajectory here, then we'll see that for the particles that travel from the outer wall of the inlet, right, they'll follow a similar trajectory and get collected by the inner wall of the outlet. So the same thing for here, which is on the other boundary, right? Particles with the same perfect electrical mobility, they can follow this streamline here, or they can follow this trajectory here and also get collected, right? This is what happens to this transfer function. Right, with this perfect electrical mobility, that's 100%. What if the particles have a smaller size? So if the particles have a smaller size, then they're going to divert to the upstream location, right? Because their electrical mobility is going to be larger, right? So they move faster towards the center electrode. But then if the particle size is just smaller by a little bit, then you can imagine that there will be some particles that can still get collected, right? Because, for example, the particles along this outer wall of the inlet here, they can get diverted a little bit, but still get transferred in, right? The extreme condition that's corresponding to the particle classification is going to be particles following this line here, right? So this is kind of like the extreme condition that particle with the smallest, so basically this is going to be the smallest mobility, the largest electrical mobility of a particle that can be classified, right? Because it enters along the outer wall of the inlet and then gets sampled by the inner wall of the inlet, right? So then you can imagine if we try to plot it in the transfer function again, omega, right, ZP. Again, you have the ZP star in the center. And then there's going to be some specific electrical mobility. And starting from that electrical mobility, right, everything is 0 downwards, right? So we can call this as ZP1. So the same thing for the larger particles. For the larger particles, right, if you go to the perfect case again, right, for the larger particles, they will move further downwards, right? So the extreme condition is that the particles will enter from the outer wall of the inlet and then exit through the inner wall of the outlet, right? So the particles are having this kind of trajectory. So under this situation, you can still kind of collect some larger particles. And if the particle size is further larger, their electrical mobility further slower, then they will completely miss the outlet of the DMA, right? So which means that there's also going to be a value, right, where the electrical mobility, if it's larger than the ZP2 here, then you're going to have a non-zero probability function. Okay, so it turns out that this transfer function here has a triangular shaped transfer function. So it has a triangular shaped function, transfer function, only when QA equals QS, which means that the inlet flow rate of the aerosol equals the sample flow rate that's going to the CPC, right? So when the SMPS is under this recirculation of the sheath flow rate, okay? And also it turns out that if we just write these values here, it turns out that here it has a value of ZP star minus QA plus Q sheath, QS divided by Q sheath plus QE ZP star. And here it has a value of ZP star plus QA plus QS divided by Q sheath plus QE ZP star. Okay. So again, this is just the basically analytical solution that's coming out of the basically the solution of the streamlines in this DMA system. If you want to see the derivation of this process, you can just follow this paper here, right? It gives a lot of information on the derivation. So for the balanced flow condition, which means that QA equals QS, and then Q sheath equals Q exhaust, right? So you can further simplify this to be just QA divided by Q sheath, and then QA divided by Q sheath. Okay, so basically this is how the transfer function looks like when you have the balanced flow condition. So then you may have the question, what happens if it's not balanced, right? So we know that SMPS system generally has a sheath pump that recirculates the flow. There may also be a situation where you may introduce more sheath flow than the exhaust flow, right? That's coming out of the system, which is going to create situations where QA larger than QS or QA smaller than QS. So we can just use these perfect conditions as an example again, right? If you have the QA larger than QS, which means that you're going to have a basically an equivalent condition where you have a wider diameter for the aerosol inlet, right? So because of that, you're going to have a streamline that looks like this, right? Which means that even at the perfect condition where you collect the particles based on their electrical mobility, not all of the particles are going to enter through this inlet here, right? And similarly, when you switch the electrical mobility to larger particles or smaller particles, right? Larger particles go this way, smaller particles go this way, then you're also going to see this decrease of the transfer function. So the transfer function is going to have a shape that looks like this, right? But one thing we should notice is that at the maximum value here, it is not 100% because not all of the particles will exit through the outlet here. So you can also imagine the case where you have QA smaller than QS. So when QA is smaller than QS, then you can treat it as the situation which is equivalent to the situation where you have a wider outlet diameter, right, or the wider dimension for the outlet. So this means that under the perfect condition, you definitely will reach to 100%, right? But at the same time, if the mobility change a little bit, they're still going to maintain at 100%. And further, they're going to decrease, right? So when you have a misbalanced aerosol flow and sample flow, you are going to have these trapezoidal shape or these trapezoidal transfer functions, right? So you can see these different conditions or the flow conditions, how they're going to affect the let's say the shape of the transfer function, okay? So let's say if we still assume that the sheath flow is balanced, people normally also will plot the transfer function in this normalized scale. So instead of using directly the ZP value, it will be normalized. The mobility will be normalized by the actual mobility of the particles, which kind of makes sense. Then you are going to have 1 plus QA divided by Q sheath. And then here is 1 plus, or let's say, first write it out. This one should be 1 minus. Okay, 1 minus QA divided by Q sheath flow. And then at this perfect or centroid electrical mobility, you have 100% transfer function. Okay. So further, as we introduced earlier, this ratio here should be actually represented as QA plus QS divided by Q sheath plus QE, right? So people further make definitions that we define this term as beta. So you can just represent it, like replace this term with beta. And then there's also a term, delta, that is the difference between the sheath and difference between the sample flow and aerosol flow divided by the summation of these two flows. So when the flow is balanced, right, so the aerosol flow and sample flow are matched, then delta equals 0. And then when these two flows are mismatched, right, you have a value of the delta. So basically, if you define these parameters, you could find out that we're going to have a transfer function that looks like this. Okay, so as we have introduced earlier, so this is a normalized electrical mobility, right? You have the centroid mobility of 1, and then the upper boundary is 1 plus beta, lower boundary is 1 minus beta. And then when the flow is matched, then you're going to have a triangular shaped transfer function, right? And then when the flow is mismatched, you're going to have a trapezoidal transfer function. Okay? So then we can also see whether that match with our analysis. So for example, when QA is larger than QS. If QA is larger than QS, we said that it's going to have the situation that looks like this. Right? You have more flow, but not all of them are going to reach to 100%. And when QA is smaller than QS, you have 100%. Right? So if you have QA larger than QS, then what happens is that you have a delta that's smaller than 0. Right? So if delta is smaller than 0, it means that here you're going to have a value that's smaller than 100%. Because the absolute value of delta is going to be positive, and then in the denominator you have a value that's larger than 1, right? And then when QA is smaller than QS, so we mentioned that for that trapezoidal shape, it's going to be 100% everywhere at the top, right? So you see it is actually 100%. So this actually agrees with what we assumed in this system here, right? So then basically even for this radically complex transfer function, there is a numerical way to represent the shape of the transfer function that is that can be expressed in this way. Okay. So basically, it's going to be a combination of different absolute values, and depending on the relative magnitude of the beta and delta values. Right. So if you want to see this derivation, you can follow this Mark Stosenberg and Peter McMurray paper. Okay. So this shape of the transfer function is first, or this analytical solution of the transfer function is first introduced by by Mark Stosenberg in his PhD thesis. So in his PhD thesis, he has done very detailed analysis of the aerosol instrumentation system, or the sizing systems. So he analyzed the performance of the DMA, introduced the ultrafine CPC, which has basically the capillary flow that's going through the center of the aerosol tube, right, which enhanced the activation. And then he also laid the foundation for the differential mobility, or the tandem differential mobility analyzers. So we'll talk about the TDMAs later on as well. So you can see basically this person has done a lot of work in his PhD that made a huge contribution to our understanding of these aerosol sizing systems. Okay, so if you further look at these equations, you can see a subscription here, ND, right? So what does ND mean? ND means non-diffusing. Okay, so you can see until now we haven't talked about the aerosol diffusion, right? So we just assume that the particles will just flow with the right trajectory, the perfect trajectory for the particles to move, and it doesn't matter whether the particles is large or small. But in situation or in reality, the diffusion are going to play a role. So if we imagine that we're introducing aerosol from the inlet here, then if the particles are very small, let's say down to 1 nanometer, then because of this diffusion or this Gaussian distribution of the particle movement, then the particles are going to move around, right? And the smaller the particle, the more diffusive they are. They're going to move both towards the inner electrode and then towards the outer electrode, right? So that's why you're going to have this spread of the particle trajectory, which means that even at this perfect electrical mobility, where you classify the particles, you are not going to achieve 100% collection efficiency. And we call this process as the broadening of the DMA transfer function. Okay, so what that means is that originally you're going to have a, let's say, a triangular shaped, let's say you have a triangular shaped transfer function, which means that QA equals QS, right? This is omega. But because of diffusion, especially where you're classifying smaller particles, you're going to have a broadened Gaussian shaped transfer function, right? Because the particles are diffusing. So the smaller particles will diffuse to, let's say, a different location that even under a further smaller electrical mobility, you're going to detect them. And particles are also moving the other direction, which means that under higher electrical mobility, you're also going to collect these particles, right? So this is what we call the diffusion broadening of the DMA transfer function. And this is shown in here. So as we introduced in our last class, we said that the higher the voltage, the smaller the electrical mobility, right? Because you have this inverse relationship in converting from the DMA voltage to particle mobility. But further, we said that the smaller the electrical mobility, the larger the particle size. So basically, if you're using a high voltage to classify particles, you're classifying larger particles. And because of that, diffusion mainly happens under small voltage, right, under low voltage values. For example, when people are using these TSI long DMAs, that's the long DMA that we disassembled in our last class, you're going to have, and when you operate it under beta of 0.1, which means that QA divided by Q sheath, or let's write out the full expression, right? QE equals 0.1. Further, if we assume that the flow is matched, then you have QA divided by Q sheath equals 0.1, right? So under this situation here, then if you reduce the voltage from 10,000 volt to 1 volt, right, you can see that the transfer function looks very different. And that's because at this low voltage here, the particles are becoming so diffusive that you don't have a like a well-defined transfer function anymore, right? So one thing that we forgot to mention is regarding how narrow the transfer function should look like. Okay, so if we go back to this transfer function here, or go back to this transfer function here, right? So we said that if we are plotting it under this normalized scale here, then you're going to see a transfer function that has a value of 1 minus beta on this point, 1 plus beta on this point. And further, people define a parameter called the full width at half maximum, right? Okay, so you see that the full width at the half maximum is just this value minus this value and divide by 2, right? You're looking at 50%. So people use this distance or use this length as the width of the transfer function. So that is going to be 1 plus QA divided by Q sheath minus 1 minus QA divided by Q sheath, and then you divide that by 2, which is QA divided by Q sheath, right? And further, people define the resolution of the transfer function. Basically, that is the centroid mobility divided by the width of the transfer function. That is 1 divided by QA over Q sheath, which is QA divided by Q sheath divided by QA. Okay, so this is the same when you're trying to calculate the resolution of the peak under the actual electrical mobilities. So as we mentioned here, right? So you can also calculate what is the full width at half maximum. So that is QA divided by Q sheath multiplied by ZP star, right? So this is the width. And then people use this centroid value divide by the width of this transfer function. You can see that it is still Q sheath divided by QA. So basically, the resolution is the intrinsic parameter that's related to how wide the transfer function is, right? And also you could notice that the transfer function is just the ratio between these two flows here. So for example, if you have an SMPS system, and then when you use the aerosol flow, use an aerosol flow of 1 liter per minute, right? And if you use the sheath flow of 10 liter per minute, you're going to have a resolution for the peak at with a value of 10, right? If you use a higher sheath flow rate, you're going to have a resolution of 100, which basically means that the transfer function is becoming narrower, right? You can use a sheath flow 1000, then it's becoming even narrower, right? Which also means that the particles of different sizes are not going to get classified by our DMA, okay? Okay, so this is related to the width of the transfer function. And you can see how the diffusion is playing a role in broadening this transfer function here, right? So even if you use a higher, let's say Q sheath divided by QA condition, even if you use a higher sheath flow combination here, sheath flow ratio here, you're still going to face this diffusion problem that the smaller particles can get classified, right? So under this situation, there's also an analytical expression of the transfer function, okay? So it is shown in here. So basically, it's still a function of the ZP, the normalized electrical mobility, the beta, the delta, and now you have a sigma value. So the sigma is dependent on the geometry of the DMA and also a normalized diffusion coefficient. So the normalized diffusion coefficient is further related to the diffusion coefficient of the particle and the flow condition. So here, in this paper here, again by Stosenberg and McMurray, so the QM and QC are just the QE and Q sheath. Okay, exhaust and sheath flow. So these are just different ways to represent them. So in this paper here, they also showed how the transfer function looks like. I think this is based on the calculation here, okay? So you can see the non-diffusing condition, and when you're using sheath flow ratio of 10, right? So we have the sheath flow at 15 liters per minute and aerosol at 1.5 liters per minute, then you have an ideal resolution of 10. But because the particles are diffusing, right, when you're introducing 3 nanometer particles inside, then you're going to have a broadening of the transfer function, right? And then even for the TSI 3085, that is a nano DMA, which we talked about, like long DMA is a long one, nano DMA is a short one to suppress diffusion. You're still going to have certain amount of diffusion in there, okay? So people have also tried to show the transfer function or the resolution of the transfer function as a function of the volts or the voltage being applied onto the DMA. So we introduced earlier that the higher the voltage, the larger the particles being classified, right? And because of that, you see the resolution is just going to reach a plateau when you're trying to classify particles at larger voltages. And then the resolution is going to get worse, right? Going to decrease when you're decreasing the voltage down. And different DMA systems are going to have different, let's say, different resolutions depending on the flow, the geometry, and other parameters. Okay, so because of that, when you're trying to classify, let's say, 5 nanometer particles, and then also to further achieve certain resolution, then you have to find out the right combination of the flows you should use. For example, here, you can see that if you're trying to classify, let's say, for example, 10 nanometer particles, okay? When you're trying to classify 10 nanometer particles, then by using different flow combinations, you're going to have different resolutions here. If you want to achieve a resolution of at least 5 for 10 nanometer particles, right? This means that you have to use a resolution, or you have to use a sheet flow ratio of 0.01, right? Or between 0.01 and 0.05. Okay, so the better the resolution, the more accurate it is for the particle size classifying. Okay, so this is another table showing you the different geometry factor that's related to the diffusing or the diffusion broadening of the DMA transfer function. Okay, so based on the discussion of the transfer function, so you can see that not all of these monodispersed particles are being classified as the same when you fix, let's say, put it in another way. So not all of these, let's say, particles being classified at certain voltage are going to have the same size, right? Because you have this triangular, or let's say Gaussian shaped transfer function, that even when you're fixing the DMA voltage to be this value, then particles of different sizes are going to get classified. So then you may have the question, so why can't we just enhance the resolution? So we mentioned that the resolution is just a ratio between the sheet flow and aerosol flow, right? So why can't we just make this sheet flow to be, let's say, 1,000 or 10,000 times higher than the aerosol flow? Can we do that? Right? We could. So this is actually the foundation of a lot of these high-resolution DMA systems, but there's a limit, right? So for example, eventually we're going to use a CPC to classify or to measure the concentration of the particles. And generally the CPCs will have a sheet flow of around 1 liter per minute, or some of them have 0.3 liter per minute, right? And because of that, so one thing we should do to enhance the resolution is to increase the sheet flow, right? So if we increase the sheet flow, one thing is limited that we can't use a very high value is related to the power consumption, right? By using a higher sheet flow rate, the power will be higher. And also you're limited by the, let's say, the laminar flow regime. You don't want to change it to the turbulent regime. But at the same time, there's a limit, or there's a more important reason that we don't want to use a high sheet flow rate. It's related to the counting statistics. So basically, when you're trying to have a very narrow transfer function, right? If you think of the extreme condition that you just have almost a thin line of the transfer function. What this means is that at this mobility, you're going to collect very few particles, okay? For example, let's say, because eventually it's the sheet flow that's diluting the aerosol flow, right? So basically it means that you're only going to collect a very small fraction of the particles, and then if the concentration of the particles are too low in that very narrow size range, then the CPC is not going to give you the correct value, which means that CPC have to sit there and then keep collecting for a long time. So that's related to the counting statistics and further related to the accuracy for the size distribution measurement, right? So then basically this is how the transfer function is going to affect our particle measurement. So as you can see, it's getting more complicated than we thought. We thought that if we fix the voltage, then we just get the concentration of particles with a specific size. But it turns out that it is not a specific size, it's a size range, right? Are there other factors that we need to consider when calculating the size distribution? So the next factor we need to consider is related to the charging of the particles. As we introduced earlier, to measure the particles with a DMA, you have to charge these particles. If you can't charge them, if they're neutral, right, they will just follow the sheath flow, right, getting compressed near the boundary or near the outer wall, and then there's no way they can get separated or classified. Right? So regarding diffusion charging, people use these Fuchs theory, okay, because it was first solved by Fuchs in 1963. So basically, the way the Fuchs charging theory works is that it considers the physical movement of the ions, and then just treat these ion particle interactions on like a single collision by collision basis. So what happens is that assume that the ions are just entering the, let's say, the surrounding or the vicinity of a particle that's sitting inside, right? And then we assume that there's an imaginary boundary that's surrounding the particle, and we call this sphere as a limiting sphere. So basically, outside the limiting sphere, the ions will just move by diffusion, right? So inside the sphere is going to be a case-by-case discussion of the particle trajectory. So basically, when you have attractive force, right? So even if the particles are moving this way, not directly facing the particle, right? They will still get collected or get captured by the particle because of the attraction. And when the particle and the ions are carrying different carrying the same polarity of the ions, even if the ions are shooting directly towards the particle, and then because of the repulsive force, they are going to get diverted, and there's no collision. Okay, so there's a way to calculate the combination coefficient between the ions and particle interaction. We call that coefficient as the ion particle combination coefficient. So basically, you can see that this coefficient is going to depend on the ion polarity, right, and also the particle polarity. At the same time, it depends on the number of charges that's carried by the particle. Okay, so if you think about the bipolar diffusion charging, so basically, when we're trying to introduce particles into this neutralizer here, as we introduced, there are positive and negative ions, right? And then for this Fuchs charging theory, it further assumes that the particles reach to the steady state charging, which means that the particles getting extra ions let's say the number of particles getting extra ions is equal to the number of particles losing the ions. Okay, so they reach to this dynamic steady state here. Okay, so while they're capturing ions, they're also losing ions. So this way, the concentration of particles with different charges are maintained constant. Okay, so then we could consider how the particle charges is being transferred, right? So for example, here you have a neutral particle, they can gain their charge by colliding with a positive ion, right? They can further gain a charge to +2 by colliding with a positive ion. But they can also gain in concentration by a positive particle colliding with a negative ion, right? And then this +1 particle can be gained by +2 particles, +2 particles colliding with negative ion, so on and so forth. And the same thing happens to the negative side, or negative charging side, right? So basically, we can try to set up an equilibrium, or try to set up a population balance for particles with different number of charges, right? So what we can do is basically, let's consider particles carrying p charges, And the p charges here, they can carry both positive charge and negative charge. And if we just consider the positive charge here, right, let's ignore this negative sign here. Okay, just look at the upper sign. So the particles carrying positive p charges, let's assume it's just +2, they can be gained by a positive 1 charge, basically p minus 1 charge colliding with a positive ion, right? They can be gained by p plus 1 charge colliding with a negative ion. And then they can be lost, their concentration can get lost by themselves colliding with a positive charge or themselves colliding with a negative charge, right? So if you build up these equations, you're going to see, so basically p minus 1 charge colliding with a positive charge, as we introduced earlier, we'll just ignore this lower sign here, right? Because if you use a different polarity, they're going to be the same, right? It works like that. And then this p plus 1 charge is here, right? You can ignore this lower charge here. Okay, and then their concentration can get lower or can get lost because these particles are colliding with ions of positive charge or negative charge. Further, these eta value here are just the ion combination coefficient, right? The ion combination coefficient is solved by the Fuchs limiting sphere theory, and that's showing here. So basically, this combination coefficient is related with the electric field that's surrounding this particle here. It's related to temperature, it's related to the diameter of the limiting sphere, the velocity of the ions, which is further a function of the mass of the particles, right? And alpha is some values related to the ion and particle properties. And then here you also have the diffusion coefficient, which is a function of the mobility of the particles. Okay, so basically, this is how we can determine the ion particle combination coefficient, and we can further use that to calculate how does the concentration of particles with different number of charges going to change. And further, I should mention here that the 2 and 1 just represents repulsion and attraction. So 1 is attraction, and then 2 is repulsion. Okay, so and then we said that, well, for the Fuchs charging theory, this is assuming that the particles with different charging state is under steady state, which means that their concentration is 0. So because of that, you can set this equation to be 0, and if you can further see that the concentration here, they can be rearranged as a ratio of the particle concentration, right? So you can rearrange it to be particle concentration, the concentration of particles carrying p charges over the concentration of particles carrying p minus 1 charges. And you can see that this one is directly related to this function here, the concentration of particles carrying p plus 1 charges over the concentration of particles carrying p charges. So this is kind of like an iteration process, right? So the ratio of particles carrying 2 charge over the ratio of particles carrying 1 charge is dependent on the ratio of particles carrying 3 charge over the particles carrying 2 charge. And further, it's a function of the concentration ratio of particles carrying 4 charges over 3 charges, right? So you can build this iteration here. So basically, if you have this relationship here, and then you can basically multiply all the way down, right? Multiply it all the way down. Let's say NP minus 1 over NP minus 2, all the way down to N1 over N0, right? And you can have basically a multiplication of all of these factors. And each of this factor is defined as as this term here, the concentration ratio, and then it's further shown as this one, right? So each factor is shown as, or can be calculated using this equation, okay? And further, one thing we should notice is that, well, the number of particles number of charges carried by the particle is limited. For example, when you have 100 nanometer particles, right? And then at maximum, this particle is just going to carry, is not going to acquire unlimited number of charges, because you have both positive and negative ions, right? So if you have these particles, they're not going to have billions of charges, right? So there's always a limit of how many charges it can have. And normally people will assume that particles have less than 20 charges in the submicron range. And it is indeed that case, right? So because of that, at certain number of J here, you're just going to have this value equals 0, which means that if you have a known value here, then you can back calculate what is A. Let's say you can first if you have a 0 here, right, which means that J equals, when J equals 19, this value is 0. The rest of them are known values, right? Ion concentration and then the combination coefficient, these are constants. This means that you can solve for what is A19, and then you can solve for what is A18, all the way down to A1, right? And because of that, you can solve what is the concentration of the particles, right? And then basically, you can find out what's the concentration of particles with any charging state. And then you could also calculate what is the total concentration of particles, because there's also neutral particles, right? And then you could calculate what is the fraction of particles carrying certain charge over the total number of particles carrying certain charge, right? So this is how we can solve the fraction of particles carrying certain charges, right? And we also call this as the let's say the charging efficiency. And one thing we should notice is that the charging efficiency is different for particles with different sizes. So here we're just assuming that particles have the uniform size. So the charging efficiency is further a function of the particle diameter, right? Which means that they're going to have different charging efficiency at different particle sizes. And we call this distribution of the charging efficiency as the charge distribution. Okay, so this is how the charge distribution looks like for a bipolar charging process. So basically you can see that it is indeed a strong function of the particle size, right? When the particle size is very small, let's say when it's carrying -1 charge, right? And you can see that the fraction particles with a size of 1 nanometer only has a probability of, let's say, let's say this is 0.5, right? I think this is 0.5. Okay, so for 1 nanometer particle, there's only 0.5% of a probability that particles carry +1 or -1 charge, right? And then for the particles of larger sizes, so you can see if it's for 100 nanometer particles, right, it has a charging efficiency of more than 20%. Okay, so basically, if you directly look at these charge distributions, and by the way, these solid lines here, these are the charging efficiency that's calculated by the Fick's theory, and these dotted lines are from the experiments. So basically, they're determined by Whedon, Solar, and Fison. Again, these are big names on the particle charging theory. So you can see that these measurements really give very good agreement with the charging theory. Okay, so from these charge distributions, you can see that there's indeed a very strong size dependence. For particles of small sizes, their charging efficiency is very low, right? It only starts, let's say, the charging efficiency is more than 20% when the particles are above 100 nanometers. And also the fraction of the charge, here the fraction of the charged particle is very low. So the fraction of the particles carrying multiple charges becomes more substantial when the dP is greater than 100 nanometer. So you can see these are the charging efficiency of particles carrying +2 or -2 charges. So you can see that their ratio are actually below 0.1%. You can neglect them when, let's say, the particle size is below 20 nanometers, right? So the fractions of multiple charging is really small when the particle size is relatively small. And also you can see that there's slightly higher fraction of negatively charged particles. So for example, for n-1 or particles carrying -1 charge, it has a higher value compared to the fraction particles carrying +1 charge. And the same thing here for -2 and +2. So the reason is that for the ions that's generated from either the neutralizers or from soft X-ray or in our ambient environments, these negative ions have smaller sizes and larger, let's say, larger electrical mobility or larger diffusivity. Okay, so their mass is smaller, and also their mobility is smaller for these ions. So that's why their mobility is larger. Okay, so these ions are basically more mobile, so they can carry or they can charge these particles more easily. Okay, so I'm just introducing a related study that's done by our group. So Shinakia has been studying the ions generated from the flame conditions. So we're trying to understand how the particles are being formed under these combustion environments. And then the flame itself generates a lot of ions. So it's a kind of a weak chemical ionization source, right? And these ions can get charged onto the particles and further affect their charge distribution. So basically, Shinakia used our high-resolution DMS system to measure what is the mobility. So basically, we could repeat the calculation over here to calculate what is combination coefficient, and then use these equations to find out what is the charged fraction or the charge distribution of the particles. So then we calculate the condition under the high temperature scenario, where the flame is actually lighted, and then under low temperature condition, which is more like a room temperature condition. So you can see that under high temperature condition, more particles are getting charged compared to the ambient condition, right? This is also understandable because under high temperature, the particles or the ions are becoming even more mobile. So it's easier for them to collide with the particles and further charge the particles. So this happens for both polarities. But again, you can see that we saw particles with smaller sizes when we're monitoring the negative ions compared to the positive ions. Right? The positive ions are less mobile, so they charge the particles with a lower efficiency. Right? So you can see the +1 is here, and the -1 is here. Right? So this is about the charging. So then most of the scenarios, people will use these bipolar diffusion charger to monitor the ambient aerosol size distribution. So because of that, people could just assume that the charge distribution is what's being predicted by the Fuchs charging theory, right? So under this situation, we assume that the charge distribution is unchanged because we're just doing this these measurements under room temperatures, right? So because of that, people find out these empirical fittings to predict what is the charged fraction for particles of different sizes. So because of that, so with that empirical fitting, people don't need to do this calculation every time anymore. You could just use these equations to find out what is the charged fraction of particles at specific size and also at specific charging state, right? It can be plus or minus I charges, okay? So in terms of generating these ions, there can be different radioactive sources. So as we introduced earlier, you could use the alpha radiation or alpha particle. That is basically just a helium nucleus, right? So these particles are relatively light and they're very easy to charge the particles. So basically, a very commonly used radioactive source generating alpha particle is the polonium source. The polonium source is relatively cheaper, right? And also it has a shorter half-life time. And then there are also sources generating beta particles. Basically, these are just electron generated from the radiation, right? So the commonly used one is just the krypton. So they have different half-life. So krypton has a half-life of 10.76 years, and polonium has a half-life of around 140 days. So that's why the polonium source need to replace more often compared to the krypton source. Okay, so in general, people will not replace these sources until they're, let's say, twice of the half-life, or basically as long as there are sufficient ion concentration being generated from the neutralizer, we can still use these neutralizers. Okay, so as we have introduced earlier, these radioactive materials may lead to safety concerns. So that's why people invented these newer soft X-ray neutralizers, which is using these X-ray sources to ionize the particles. So apart from diffusion charging, there's also unipolar charging. So unipolar charging is less frequently used by these aerosol sampling systems, mainly because it's kind of difficult to predict the charge distribution. And also this charging process is dependent on the ion source properties and also the residence time of the particles in the system. So here it gives a simple diagram of the unipolar charging system. So what it uses is a corona wire that's under a high voltage. And then because of the high voltage, it's going to ionize the air surrounding the wire here. So if it's carrying, let's say, a positive high voltage, then it's going to attract all of these positive ions to the wire and eject negative ions to the outside. Right? And at the same time, you introduce aerosols here, get the particles charged, so you can further monitor what's the size distribution of the particles. So again, if you think about this process, we mentioned that for the bipolar charging, you have this charging process in two ways, right? You can create multiply charged positive particles and multiply charged negative charged particles through this collision process here. And it's the same process for the unipolar charging, except that now, since you only have ions of one polarity, you can only charge the particles in one direction. So this is assuming that it's charging the particles with the positive ions. So you're going to have 0, plus 1, plus 2, and all the way up. So you can build up the population balance for these each polarity, or let's say for the particles with different charging states. So, and actually these equations are analytically solvable. So they have analytical solutions. So it's not like the analysis for the bipolar charger where we have to assume a steady state. For this system, it's never under steady state, right? Because you have a limited amount of ions. They can charge the particles to, let's say, a very large number of charges carried by the particle. Okay, so you can see, you could calculate what is the concentration of particles carrying a specific number of charges, but very importantly, you can see here it's a function of the time. So because of that, when you design the unipolar charger, you have to consider how the flow looks like. So there's going to be particles with different trajectories, and therefore it's kind of difficult to control the charge distribution of a unipolar charger. So that's why people would still use the bipolar charger to give the particles a known charge distribution. Okay, so here it's further showing you the, let's say, the charge fraction of particles with different, let's say, with different charging efficiency of particles with different sizes, right? So you can see particles with larger sizes can be more easily charged. Particles with smaller sizes, particles are less easily charged. Okay? So here at the end of this class, we'll briefly talk about how we convert the CPC measurement to the size distribution. Okay? So here I'm just showing you this schematic diagram of the DMA operation again. So we're basically introducing the aerosol flow here. We have the pumps to pull the sheath flow and introduce the sheath flow, and then the aerosols are being introduced to the CPC, right? So we introduced that the DMA voltage can be converted to particle size, but it seems that the CPC concentration, to convert it into the actual, let's say dNd log dP, it's way more complicated than we thought, right? So we need to consider these factors. First, the transfer function. So we saw from the transfer function that not all of the particles with the same sizes are being classified, right? There's always some particles with different sizes getting classified by the DMA. So then how do we find out the size distribution at this specific, let's say this centroid or perfect electrical mobility? And also not all of the particles are getting charged, right? We have this charging probability, right? So particles, only a fraction of them are getting charged, right? So how do we find out the uncharged particle concentrations? Because eventually when we talk about the size distribution, we don't care whether they're charged or not, right? So there's also CPC particle detection efficiency. We introduced in our earlier classes that the CPCs are not seeing all of the particles. This is especially the case when we are talking about the small particles, right? They're not being activated. And furthermore, there's sampling loss. When you're talking about particles, let's say smaller particles being transported in the system, then you have the diffusion loss, especially, let's say, particles below 10 nanometers, then they get lost when they are being introduced to the DMA, right, here, and then when they are being introduced to the CPC. You also have particle loss here. So because of that, we need to consider all of these factors together. So again, this is showing you this paper by Stolzenberg and Peter McMurray. So this data inversion problem has been discussed over the past few decades, and there are different algorithms to consider these effects. I'll just start from a relatively simple method, and then I'll talk about the more complicated method for the data inversion. So if you consider the response of the CPC, right? Let me write out the authors for this paper. Okay, this is 2008. I also showed this paper earlier in this class. So if you consider the CPC response here, right? So that is related to how much aerosols you take in or how much sample flow you took in. And also, as we introduced, it's related to the CPC detection efficiency, the transfer function, the charging efficiency, right? And it didn't consider this penetration efficiency, but you could if you just multiply this, let's say the diffusion. Let's just use D, right? It's a function of dp, right? And further, since you're you're integrating it based on the mobility, so you could directly write ZP, or initially you could write you could write ZP, or let me see. So since this is integrating the particle concentration, right? So this, you should multiply it by dn, right, in the end. Okay, so further you could make some derivations that you split or you multiply d log dp on both the numerator and denominator, right? So you multiply that, and then you multiply this term here. So basically you're converting the integration of the particle concentration or the size distribution to a let's say to the integration of the particle electrical mobility. Okay, and this term looks kind of familiar, right? This is the size distribution you're asking for. Okay, so for this relatively simple data inversion, what it assumes that there's no multiple charging. So basically particles carry at maximum one charge. And since the DMA classified particles based on charge, you could just assume that this n term equals 1, right? Originally, this is a summation to represent the multiple charging effect. So now you could just assume that this is 1. And then you will simplify it to this equation here. Okay. And further, what this inversion method assumes is that if you consider the transfer function is a relatively narrow triangular, right? This is assuming that this is a triangular. And if you look at the particle, the CPC detection efficiency, or the charging efficiency, or the particle size distribution, they're all relatively constant in this narrow range of the transfer function, right? What this means is that since this is an integration right? This is trying to integrate particles from all different size ranges. You could just specify or assume these are constants over the narrow range of the transfer function, because outside your transfer function is just zero. You don't need to consider all of these factors anymore. Only between these transfer function, you could assume that these factors are constants, which means that you can take them out of this integral here. Okay, if you take them out, then you have the charging efficiency, CPC efficiency, and the size distribution outside, and then you just have the integral of the transfer function. And further, this term here, you can directly calculate what is the derivative here, because you know the relationship between particle size and ZP, right? Further, ZP tilde is just ZP divided by the or normalized by the centroid particle mobility, and this is just a constant, right? So you know the relationship between these two, you can directly calculate what this is. So that's also constant. You can treat it as a constant in the narrow range of the transfer function. You can take that out as well. And finally, it's just the integration of the transfer function. And we know that the integration of the transfer function, since we already know the shape, right? If you go all the way back, since you already know the shape, right? And then if you plot in the normalized scale, right? You're integrating the normalized scale, and then you know the base. The base is just 2 beta, right? You know the height, that's 100%. So the area is just a beta. Okay, so basically you get this beta out, and then by further rearrange it, you can get the size distribution. So this is a relatively simple way to do the data inversion, but you can see a critical problem is that it ignores the multiple charging, right? Although this is a relatively straightforward way to calculate it, right? But we said the multiple charging is becoming an issue when you have particles with sizes above 100 nanometer, and this is also an important size range we're interested in. So in order to do that, we need to do a full version of the data inversion, right? So again, the response of the CPC is going to be a function of all of these parameters, right? Then let's say the penetration efficiency, this time we're adding it in, the CPC counting efficiency, the particle charging efficiency, and then the DMA transfer function, right? So further, you have to consider the particles with different charges, and then you have to integrate it with particles from the smallest size to the largest size, or basically here it's shown as the log, right? So for particles with the smallest size, log is going to go from negative infinity. A particle of largest size is positive infinity, right? So this is the integration. And further, what we can do is we can separate this range here to be in the a different size bins, okay? So basically you can separate it into multiple size bins, and then changing this integral to a summation, right? With into, let's say, into k number of bins, and then you basically will classify it, right? And you consider the integration in different size bins. Okay, so this is a conversion over here. And further, again, you can make the assumption that the size distribution function is relatively constant over this transfer function regime, right? Because you only consider the transfer function. So the transfer function only has a value in its narrow range here. So you could move the dp out, right? And then it's going to be the response of the CPC is going to be a summation of particles in different size bins, right? At different size bins multiplied by this whole term here. And this long term here is a constant, okay? So basically, you can see that the response of the CPC is dependent on the concentration particles in different size bins. And then for different size bin particles in different size bins, you multiply a different factor here. So basically, if you further write it out, it's going to be Rj equals a series of factors multiplied by series of, let's say, a row of factors multiplied by column of size distribution functions, right? So you could show that in this matrix form. So basically, R1 is this term multiplied by size distribution, R2 is this term multiplied by size distribution, so on and so forth. So you could have this matrix form of the response here. So now the questions converted to, if you know the response of the CPC, how do you get the particle size distribution? Okay, so there are different inversion methods. There's this the 2-me inversion method. It was first made by or published by Toomey in 1975, right? So this is an iteration-based method that gradually converged this n to be the size distribution. And also there's this non-negative least squares matrix inversion that's published by Lawson Hansen method, right? Also converting, let's say, to directly solve this matrix calculation here, okay? So this is how the more sophisticated data inversion method looks like when you're trying to convert the size distribution, or when you're trying to convert the CPC responses to the particle size distributions, okay? I think we can stop over here regarding the SMPS data inversion. So as you can see, this is a relatively complicated problem, but we do have a solution. And unfortunately, due to the scope of this class, I can just talk about the general information of these data inversions, but there are many papers talking about how you can calculate the size distributions based on these inversion matrix or based on the CPC operating conditions. You can feel free to go through those papers. And also, this data inversion not only happens for the SMPS. So we need to consider the data inversion also for different types of aerosol size distribution measurements. For example, the APS, and then for example, the CPMA that we introduced earlier, right, also monitors the mass-based size distribution, right? So no matter which instrument you have, you need to consider the transfer function and also the data inversion, right? And if you talk to, let's say, the vendor or the scientists creating these instruments, data inversion is always their top priority, which is to convert the response of the instrument to the actual measured value related to the aerosol property. Okay, so that's it for this class. Feel free to let me know if you have any questions. Thank you.